Hello and welcome. Today we're going to watch a few sorting algorithms written in assembly language work on bytes in the text buffer, so you can see things rearranging themselves in real time. And we're going to use BASIC's timer to compare how fast they all are. The source code for all the code you can find in a link in the description. And before we start, one thing to be aware of: while I was recording this, I ran into an issue using timer, and I misdiagnosed that issue as one of two possible things, neither of which were true. And I decided to leave all that in because you can sort of watch me investigating these different possibilities and then finally dawning on me what was actually wrong. And you perhaps can spot the bug before I did. So I hope you find it interesting. Let's go! In order to compare the timings between the different sorting routines, I figured why not just use BASIC's timer? I've got the BASIC ROM, let's use it, like always. So the timer function is over here, and it's pretty simple. All it does is it takes this magic memory address, put the value from that address into X, and then just use the floating point accumulators to convert that into an integer that can be returned back to BASIC. So really the secret sauce is this TIMVAL. And just above the timer routine is how TIMVAL gets updated. So it gets updated through an interrupt. The main code is here, where we grab the current value of TIMVAL and stick it in X. We then add 1 to X, and then put that back into TIMVAL. So the interrupt, which is interrupting any code that's running at any time on a particular interval, just goes ahead and updates that value. And if it wraps around, it wraps around. So in theory, all I really need to do is just directly go into that address to get the timer value. And I could clear it anytime I want to. I could grab the current value anytime I want to. And this interrupt will dutifully continue to increment it on a regular interval. So where is TIMVAL? TIMVAL is at hex 112, which is also where user jump is, which seems a little strange, but the idea is that this is only used by the vanilla original color basic, and this is only used in extended basic and on. So they just decided to take something that they stopped using in color basic and have that address then be repurposed for TIMVAL. It's 3 bytes long, but only the first 2 bytes are actually used by the timer. The third byte isn't used. So let's take a look. I'm in MAME and in the debugger, and I'm going to grab hex 112 and I'm going to take a look here at these values and see what happens. So we're just stopped right before the boot up sequence begins, and so let's go boot up. And here you can see very clearly it is increasing at what appears to be a regular rate. And so it seems like a pretty safe thing to use. And just for fun, we've done this before, but let's just do it again. Let's take a look at the timer as shown on the text buffer. If we relocate the VDG's screen buffer start to be 0, which you get when you poke a 0 into all of the even addresses here. So my guess is that it's like these. So let's see, is this really at hex 112? Since each of these lines is about hex 20 long, is exactly hex 20 long, we would count, this would bring us to 20, 40, 60, 80, A0, C0, E0, and this would be 100, yeah, 100. And then we would go 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, O, 1, 2. Well, maybe I'm off by 1, but whatever. It's right around here. So the idea is I'm going to store a sum of all of the timing ticks for each of the 3 sorting algorithms that I'm comparing. I'm comparing bubble sort, insertion sort, and quicksort. So this first word will be the total number of timer clicks that ran while bubble sort was running, and this for insertion sort, and this for quicksort. And I access them through the timing info symbol. I update them in the main loop. So the main loop runs each of the 3 sorting algorithms once per iteration. So first up is bubble sort. This is the call that runs bubble sort. And on either side of it, before it, is where I clear my timer value. And then right after it, I load the current value of the timing value into the D register. And then I stick D inside here. So the very first element of this is for bubble sort, and I add to D whatever was there already, and then I store that sum back in. If I scroll down to insertion sort, you'll see the same thing. Here's where I call insertion sort, and on either side I mess with the timer. I clear it out here, and then I grab the current value. Now I'm sticking it into +2, or I should say I take the current sum out of the second timing info, I add D to that, and then I store D back because the second entry is for insertion sort, and each entry is 2 bytes, that's why the +2. And then you'll see the +4 down here for quicksort. Quicksort's a little bit more complicated because we're pushing parameters onto the stack to facilitate recursion. I will talk a lot more about the quicksort code in an upcoming video. But the interesting part here is I clear the timing value first, then I go ahead and push my parameters and call quicksort, and then right after I retrieve my timing value, and it's in timing info +4, that I grab the current sum, add that to D, and then put D back in. So let's see what that gives us. I want to emphasize, take a look at this cursor. I am not running in turbo mode. I am not using the high-speed poke. This is all just normal. So the idea is I pick a whole bunch of random values, fill the screen with them, and I'm going to reuse this set of random values for each of the 3 sorts for this trial. So that way it's kind of a fair comparison. So this is not only stored in the screen buffer, this is also stored in another set of hex 200 bytes that I reserved in memory, so I can reinstate the screen with this later. So first up is bubble sort. Let's go. It seems pretty fast. It's pretty neat. That's all done. And there, boom. So you can see very quickly it reinstates the garbage, because calling the random number generator is what's so slow, but just copying into the buffer is super fast. And so now we run insertion sort on that same test case. Quite fast. And then reinstate the garbage, and then we run quicksort. 3, 2, 1, go. Whoa! Almost like it took no time at all. It's incredible. And let's see what the timing values are for that. So bubble sort took 498 ticks, insertion sort 424, quicksort 51. This probably kind of seems accurate. Quicksort seemed almost instantaneous. I would expect this to be way less than this, and it kind of is. Maybe I thought it would be a little less. So that's the first trial. For the second trial, we pick a new set of random garbage, and we'll reuse that for each of the 3 algorithms. So here's our bubble sort. And insertion sort. And quicksort. It's like nothing. It takes no time at all. And so now what we see is a sum. So we took the tick counts from the first trial and we added the tick counts from the second trial to it. Because I'm too lazy to calculate an average and show like the floating point numbers and stuff. I'm just keeping it all int, so I'm just adding. And so here now it looks a little less realistic to me, because according to this, quicksort is just about 1/3 of the time that insertion sort took, when it seemed to me more like a 15 1/15 of the time. It seems like it should have taken nearly no time at all, and yet look at this. These are too close. Let's do a third trial. And now the distance is a little bit wider again. I've done this before, truth be told. What you're seeing now is not the very first time I've run it. And I've had kind of radically different results here, even though the random number generator is always starting at the same seed each time. So I'm really using the same values each time. You would expect the timing to be the same. But there are a couple possible reasons I can think of why my results might be different. And one of them could be that the way the timer interrupt is coded up, maybe the way interrupts work on the 6809, maybe in general, it's just not completely reliably always the same. Maybe there's just enough other weird stuff going on where if the interrupt happens at a certain time, it might take longer I don't know. I don't know how all this stuff works, but maybe just like in general, it's unreliable. But the other possibility is, could it be that I'm using an emulator right now? I'm using XRoar as opposed to the real hardware. Would the real hardware give me something different? So I'm going to try to do a side-by-side comparison, and I'm not going to have it wait on keyboard input. I'm just going to have XRoar and my real CoCo running simultaneously, and let's see how similar the results are. So much for that theory. You can see these timings are very similar between the physical CoCo and XRoar. So maybe I unjustifiably maligned the good name of XRoar. Maybe the emulators are just fine, and there's just something inherent in the design of these interrupts that make them very unreliable. And I knew that somehow people can use interrupts when they're doing gaming and animation, where they base their drawing on the vertical sync of the VDG. And I was thinking maybe there's a way to get an interrupt straight from the VDG. I went back to the Tepolt book to read up more on interrupts, which I only understood on a very, very, very minimal basis. And I found that there's several kinds of interrupts, but there's only one IRQ that Color Basic subscribes to, and that comes from this PIA1, and it has two potential signals coming into PIA1, CA1 and CB1. This is every 63.5 microseconds, very, 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 very frequent, and this is every 16.7 milliseconds. And lo and behold, they're both generated from an electrical signal from the VDG. So I'm already using the most reliable signal at the most reliable interval. So according to this, the signal from CA1 is so fast and so frequent that it's basically too fast to be of much use. And it talks about how much time the CPU would have to process instructions between the interrupts. So this must be the horizontal sync. So this must happen for every line, and this must be the vertical sync or the frame sync, which happens once per frame for the whole screen. And sure enough, it does happen 60 times a second. So if I'm reading this all correctly, the timer gets updated from the IRQ with this frequency, and so the timer should be updated 60 times a second. And maybe that's even stated in the Color Basic manual. I don't remember. I could look it up. But why not just verify this? So I'm just going to write a tiny little program to test this. So when I run this, it should show a bunch of decimal numbers. But the ones digit should ascend about once per second. Since I'm dividing timer by 60 and there's supposedly 60 of these per second, I should get about 1 per second in terms of changing the ones digit. 45, 46, 47, 48, And so I figured, okay, this does seem to be about 6 times per second. Looks like the Tepolt book is telling me what's really going on. But let's just double check in Unravelled. Let's really just read a little further and make sure that this IRQ is happening the way I think it is. Here is extended basics IRQ routine. These are the lines that update TIMVAL. You load it into X, you add 1 to X, you put it back into TIMVAL. And this starts here at XIRQSV. And here is where XIRQSV gets stored into the vector. So I assume this is a RAM vector that the IRQ is set up to call. So IRQVec is 3 reserved bytes. My guess is the very first byte is a jump instruction, and then the reason it was adding to or storing into IRQVec plus 1 is because that's where the address is. And sure enough, it's showing us like it was with the RAM vectors for Putcher in a previous video. They'll tell us like with each different version of BASIC what addresses end up getting stored there. And you'll see that these are stored at 010C. And in the Tepolt book, 010C appears to be hard-coded as the effective address of what gets stored in ROM at FFFF8 and FFF9 for the IRQ. So my guess is that the CPU just knows to look for what's at these addresses to handle the IRQ, and then those addresses just know to hold this address. I guess that's just all hardwired somehow. And then the first place that either BASIC or programmer gets into the picture is if we start hacking at 010C, which I'm not doing, but BASIC is doing on my behalf. So the long and short of it is that it seems that by using the timer value, I am using something just as accurate as the VDG is using to synchronize the screen. So did I just write a bug? Like, if the emulator's okay and the design of the color computer is made to be extremely reliable for these interrupts, is it me? So we're back at my code. You can see I've commented out all the wait for keystrokes so I could run 10 trials nice and quickly. And so I just started looking back at my code again, and that's when it completely dawned on me that I do have a bug, and it's right on your screen. Do you see the bug? You see the bug? The part where I use TIMVAL to update my timing info gives us a clue. I load TIMVAL into D. I load the address of the timing info into X. And then I add whatever is at X to D. D, that good old 16-bit register. How do I clear the TIMVAL? I clear it by using the CLR opcode and by hoping that the 6809 is a mind reader and that it knows that I treat this address as the location of a 16-bit value. It's not a mind reader. When you feed it an address, it treats it as the location of an 8-bit value. I'm only clearing the most significant byte of my timer. Okay. So what I really meant to say was, boom. This should reset all 16 bits. All right, let's give this a try. Now if we take a look at our numbers, this is a lot more like what I was thinking. This is not quite a 15th of this, but this is a 10th of this. So that's pretty good. And this, by the way, looks a lot smaller than this compared to before. Let's add a few more trials and see what we get. And there we go. After 10 trials, insertion sort is less than half as long as bubble sort, and quick sort is less than 1/10 as long as insertion sort. Okay, this I believe. over the course of 10 trials. If it took 170 tick counts, you divide that by 60. So it spent a whole 3 seconds on quicksort over 10 trials total. That's not a whole lot compared to these others. So this is what I was trying to do all along, is to prove that quicksort is quick.